Hello, this is AMET 104 lecture recording week 10.1. So last class we went over chapter 16.2, and that was permutations and combinations. And today we're just going to go over different examples that you might encounter. So I did prepare several different problems, but I'm not sure if we actually have enough time to go over everything. So without further ado, let's start with an example. Say a state license plate starts with a digit other than 0, followed by one capital letter, followed by 5 digits. So this is just an example. So if the problem asks, how many different license plates are possible? So it looks like in the state license plate, we have the first digit, which can vary from 1 through 9. It says excluding 0. And we have one capital letter, which is through A through Z. And we have 5 digits, 1, 2, 3, 4, 5. And all of these could be either from 0 to 9. So we know that in the first digit, we can only have 8 different numbers. So we have 8 different possibilities. And for the second place, there are 26 letters. And from third and on, for each digit, we can have 10. Ooh, my mistake. Here we have 9. And for the rest 5 digits, for each digit, we can have 10 different choices. And knowing that, we know that by multiplication rule, you can simply multiply each one and simply find the number of possible ways. So in this case, it's a 23,400,000. Then what if a problem asks, how many different license plates that start with a 7 and end with an 8? So starts with 7 and ends with an 8. So we know that now in the first place, we don't have any choice. We only have one number, so 7. So we only have one choice in the first place. For the second place, we don't really have any restrictions. So for the second place, we still have 26. And for the following 4 digits, we have no restrictions. So we have 10, 10, 10, and 10. But for the last one, it has to be 8. So we only have one choice. And by multiplication rule, you can simply multiply all that, and that's going to be 260,000 different ways. Let's look at one last case for this scenario. So what if it has no repeated symbols? So meaning that no numbers or letters can repeat. So in this case, we know that for the very first digit, we can have 9 different, for the very first place, we can have 9 different choices. For the first letter, we can also have 26 different choices. But for the third place, because we already used one number here, 1 through 9, we only have 9 different choices. Obviously 0 was not used here, but so we can have 0, but we cannot have any other numbers that's actually used here. So we still have 9 here. And once the number is used here, we now use 2 different numbers, so it's going to be 8. And same logic follows, 7, 6, and 5. And if you multiply all that thing by multiplication rule, you have 3,538,000 different ways. I think there's 80 here. So I know the numbers are very big, and in this case, we looked at a state license plate example, but I think it was pretty straightforward. I think if you draw out a diagram, well, I'm not sure if you can even call this a diagram, if we can draw this out and see for each place how many choices we have, that's really the easiest way to go about these problems. Okay, so now let's go over to a different example. And this example is also pretty similar. So let's say in this case, Jack packs 2 pairs of shoes, 3 pairs of boots, 5 pairs of jeans, 6 pairs of dress pants, and 4 dress shirts. For a trip. then how many different outfits can Jack make with these combinations? So obviously you don't really have much guidance, but it's pretty evident that you don't wear shoes and boots at the same time. So logically speaking, how many different outfits? So how many different outfits? So in this case, let's look at it this way. So let's look at the footwear. And we also have jeans. So let's say the pants. Or if you can say just bottom. And we also have the top. So in this case, for the footwear, we have 2 pairs of shoes and 3 pairs of boots. So in total, we have 5. Let me just say 2 plus 3. So that's 5. For the bottom, we have 5 pairs of jeans and 6 pairs of dress pants. So in total, that's 5 plus 6 bottom, that's 11. And for the top, Jack has 4. So simply we can say by multiplication rule, we have 5 multiplied by 11 multiplied by 4. And that is simply 220 different outfits. And let's say if, for next one, if Jack brings 3 sweaters, that he could either wear instead of dress shirts, or on top of dress shirts. So how many different outfits? So in this case, Jack now brings another piece of clothing, and he brings 3 sweaters. And these 3 sweaters he can either wear instead of the dress shirt, so he can either choose to wear a dress shirt or sweater, or he also has a choice to wear it together, so you can wear a dress shirt and wear a sweater on top of it for the colder days. So if you're given that choice, how many different ways can Jack wear this outfit? So let's actually do that in 2 different scenarios. So let's say sweater and shirt separately. And let's look at the case where this together. For the separately cases, we have footwear, and we have a bottom, and we have a top. For the footwear, we know that we still have 5 different choices. And for the bottom, we have 11. And for the top, we know that we had 4 different dress shirts, and there are now 3 additional sweaters. And since we can wear either one of those, we're just considering as a one top. So now that's 7. So by multiplication rule, if you multiply 5, 11, and 7, you're going to end up with 385. And what if Jack decides to wear them together? So in that scenario, you still have 5 different footwear, and you have 11 bottom, and you have 4 dress shirts, and on top of that, you can wear 3 different sweaters. And by multiplication rule, that's going to be 660. So in total, if you add these two, you actually have 1,045 different ways to combine these clothings. I understand in this case, excuse me, I understand in this case it could be very confusing to, it may not be very clear why you have to divide it in 2 different cases. It's because you have different choices. You can either decide to wear them separately or together. So it's really hard to compute a single multiplication formula that's going to output the number that we want. So in this case, it's always easier to look at it separately and just go with it. I mean, and just add the 2 different cases together. So if you're given choices, separate the scenario. And combine numbers later. Now let's look at a new example. So in this case, let's say a restaurant offers a menu consisting of 3 different let's say 3 appetizers, and 3 soups, 3 salads, and 9 main courses, and lastly 5 desserts. And let's say a fixed price lunch consists of a choice of appetizer, salad, and the main course. How many different ways can you order this lunch menu? In this case, we have to choose one appetizer, one salad, and a main course. So let's say we have one appetizer, we have a salad, and the main course. Let's say that. For appetizer, we have 3 different choices in the menu, and for salad, we have 3 as well, and for the main course, we have 9. Then simply by multiplication rule, we should be able to conclude that it's 81 different ways. What if, let's say the dinner menu, let's say a fixed price dinner has a choice of appetizer, and a choice of soup or salad. So you can either choose soup or salad for this, and a main course, and the dessert. Then for this dinner menu, how many different ways can you order this? So the same logic applies here too. So we have a choice of appetizer, and we have, in this case, soup or salad. So soup or salad. And we also have a main course. And lastly, we have a dessert. So let's look at the menu here. So we have 3 different choices of appetizers. And for soup or salad, you can choose either. In this case, you actually have total of 6 different choices. So you can either choose one from any of the 6 entries. So it's now 3 plus 3, so 6. And this comes from 3 plus 3. For the main course, we have 9. And lastly, for dessert, we have 5. And if you simply multiply them all, you're going to get 810. Let's say a dinner special goes like this. You have a choice of soup, a salad separately, or both, and a main menu, a main course. then how many different ways can you order this case? So as we can see, in this case, we are given either ordering both soup and salad or separately, just one soup or just choose one salad. I know this is a really weird setup, but for the sake of the problems, let's go ahead and solve this. So we can do it in two different manner. So case one, we have either soup or salad separately, or you can have both. And in the case of ordering them separately, you again have 6 different choices, just like here. And you multiply by the number of main course. So that's going to be 54. And when you're ordering both, it means that you have choice of 3 soup and the choice of salad. So you have different combinations of ordering each together. And lastly, you also have the main course, and that's going to be 81. So if you add them together, you're going to have 135 different ways to order this. So this problem was, it was a smaller number, but I think it was very similar to the previous problem we did with the outfits. And these are pretty much the difficulty that you should encounter when it comes to multiplication rules like this. Now let's look at the next example. And this example can be a little bit tricky, and you can also solve this in a couple different ways. So let me read the problem out for you first. Let's say 5 people, and which consists of 3 men and 2 women. Line up at a checkout stand in a grocery store. And the first question would be, without any restrictions, how many different ways can they line up? So how many ways can they line up? So without any restrictions, we know that there are 5 people. So simply we can say for 1, 2, 3, 4, 5 different spots, we can have, for the first place, we can have 5 different people. And after the first person is chosen, for the second place, we have 4 different ways to choose. And for the third place, we have 3, 2, and 1. And simply by multiplying them all, it's 120. And as you can see, this is also the same as 5 factorial. Then how about in the same scenario, let's say, in how many ways can they line up if the second person must be a man? So let's say the second person must be a man. So let's actually draw the diagram again. So we have 1, 2, 3, 4, 5 different places. And we know that this has to be a man. So when you're given restrictions like this, you always consider the restriction first. Leave out the ones that do not have any restriction and take care of this restriction first. So we have 3 men in this group, and if the second place can only be a man, you can have 3 different choices here. That's what we're gonna do. So the key thing here is to take care of the restriction first. So for the second place, we have taken care of that it has to be a man. So we have 3 different choices. So after the second place is chosen, now we have 4 different spots and we have 4 different people. So now simply you're doing 4 different people coming the first, and we have 3, which is the remainder after the first place is chosen, and 2 and 1. And you simply multiply them all by multiplication rule, and you now have 72 different ways. So this is 4, 3, 2, 1 because after the first man was chosen to be in the second place, and you now have 4 different people. So it's simply the matter of ordering 4 different people. So it's a 4 factorial. It's the same thing. It just happened to be in the second spot. So you just have to skip the second spot when you're doing the 4 factorial in this case. So let's do a very similar example, but a little bit more complex. So let's say now we have 7 people at the grocery stand, and there are 4 men and 3 women. And in this case, let's say no woman at the back 4 positions. So in other words, we have 1, 2, 3, 4, 5, 6, 7 people to line up, but in the 4 positions here, no woman. Or in other words, just men in this case. So let's actually consider the last 4 spots first. So we know that in the last 4 spots we can have no women, so we can only have men in this case. So we have 4 men, 4 different spots. Then it's pretty simple that you can simply do the 4, 3, 2, 1. So it's simply 4 factorial. And now let's go to the place that we do not have any restriction. So now after these 4 spots are taken, we can see that there are no more men left, we only have 3 more people and they all have to be women. So we have 3, 2, 1. That's it. So 3 factorial multiplied by 4 factorial. If there were more than 4 men, it would have been a little bit different. We would pretty much put the remainder of people here. But in this case, we only have 4 men, so we only have to do the 4 factorial multiplied by 3 factorial. So here, the 4 factorial is simply the number of ways that you can arrange 4 men. And this 3 factorial is simply the number that you can arrange 3 different women. And by multiplication rule, you would have to multiply all these numbers, and it's going to be 144. Let's say for the second scenario, let's say they must alternate. In other words, men, women, men, women, like this. So let's actually draw this again. So there are many different ways to alternate people, but in this case, because we have 4 men and 3 women, in order to alternate the order properly, the first, third, fifth, and seventh, so in this case, all the odd number places has to be men because there are 4 men and 3 women. You cannot have a woman in the first place and keep alternating the sequence. So this has to be men, and the remainder of the place obviously has to be women. Let's look at 2 groups separately. So for men, in the odd number of spots, you first have 4 different people who can come here. And after the first one is chosen, you have 3, you have 2, and 1. In a similar manner, you can also do for women. We have 3 different women who can come here. And we have 2 and 1. And simply by multiplying all that together, you again have 144. So in this case, it turned out pretty much the same thing as the one and the previous one. So it's simply, this all comes down to ordering 4 different men into a designated spot and 3 different women into a designated spot. And problems like this, ordering a group of people, is the very typical problem that you'll probably see in the quizzes or exams. So before I let you go, let's do one more example. So far, we have done a lot of ordering, and we really haven't done a lot of permutations or combinations directly. And even though in this course, I'm not going to directly ask you to compute the combination or permutation, even though I know you can, I think it's important to go over just the concept at least. So let's say in this corporation, so the corporation example. has 30 members. And how many different ways you can choose 4 people? So how many different ways that you have to choose the president, a vice president, a treasurer, and a secretary. So if you were to obviously calculate it in numbers, you can simply say 30, 29, 28, and 27. But if you were to put it in permutation and combination, it's simply you're choosing out of 30 people, and you're simply choosing 4 different people. So it's simply going to be 30 permutation 4. In this case, it's not important to just calculate this number because I'm sure you can do it, but I just wanted to show a difference between the permutation and the combination. And in this case, how many different ways, so how many delegations of 4 members? In other words, all members are equal. And in this case, we have the same number of choices, and you're choosing the same number of people. And simply because there are no ordering and there's no designation, it's simply the same as the 30 combination 4. So in this case, the only difference here is that the permutation really has a designation. So this is designation. And in this case, also the order matters. Whereas the combination, no order, and also it's simply the choices. That's what you're more interested in. So really, it's very useful that if you knew all the formula and how to use it, and it'll make your life a lot easier in this course as well. But for the level of problems and the numbers that you'll be given in this course, you, even though it'll be beneficial, you do not necessarily have to compute the permutation and combination. But when given a problem, it is important to know which one is permutation and which one is combination. And that's really all you really need to know. So today I think I'm going to end right here. And so this is actually the last class before the second, well, last class that we go over stuff before the second exam. And next class for 10.2, I'm basically going to spend the whole class going over different formulas and different, just formulas and equations that's going to be necessary for the second exam. And after we come back, we'll probably end the rest of the chapter and prepare for the final. So thank you for joining the class. If you have any questions or comments or concern, please contact me through email. And I hope you have a great rest of the day.